Welcome back to another HVAC Engineering-Techie training video. Remember, this channel talks all things about HVAC engineering, design, construction, equipment, systems, tab, control, energy, and performance. So today we're talking about DDC controllers and network devices. This is C-2 in our training videos for controls. Now today, this video is going to actually just show you the network controllers, the network devices, how those networks operate. We're also going to show you in depth how submittal drawings and how design drawings should look like, and what the different components show on that for this part of the training. Now the next one, C3, is on network, so it's basically an extension of this one. It's not a long video, but it'll show you those components. I'd like to ask you a favor to become a subscribing member if you haven't already. Just push the button that says subscribe down below. It costs you nothing. It's absolutely free. Does help me, and if you like the videos, please give me a thumbs up. This helps me with Google. That's how they evaluate my videos. So appreciate you being here, and I hope you enjoyed the video. Let's get started. Okay, so now I'm going to review just a little bit here about the different videos that we have available. We have C1, which is HVAC Control System Basics, what hopefully you've already looked at. This video, C2, is on controllers and network devices. Just kind of explains basic controllers. Also deals with what a submittal should look like on a controller. C3, DDC control architecture, which shows you the different architectures. C4 is DDC control components and devices. DDC control installation wiring, how to wire this, what's considered quality and what's required. Water-cooled central plant system sequences, hot water control sequences, hot chill water sequence central plant sequences. Constant volume air handler control sequences, VAV air handler control system sequences, and outside air control sequences. Now my general system videos, the S videos, all cover the majority of different kinds of systems and how they operate, and it has a basic sequence of control, a real high level control, kind of tells you how the system works. These sequence videos here are much more in-depth look at exactly how the sequence should be. And I cover only the most popular systems. I don't cover all the systems in the S systems. But this will show you the different types of sequences for the different types of main systems and the details of those sequences. They also include the reset requirements from ASHRAE Guideline 36, which is a much better reset sequence that actually works. So hopefully that will become more common, where people are using that standard instead of trying to invent the wheel themselves. This wheel has been developed by different control manufacturers, and they do work well. So my goal as a commissioner was always to get them to use a factory sequence or a well-developed sequence that works every time, instead of having to go through the process of inventing a new sequence, trying to program it, and failing it 100 times before you figure out how to make it halfway work. It's much easier to use these. C12 is tuning DDC loops. C13 is how to select control valves. C14, how to select control dampers. And HVAC is the details of pneumatic control systems. All right, digital controllers. So we've already looked at this kind of network once. This is kind of the WAN, wide area network, done by the owner, and these are not done by us. Then we have connect our lower LAN, and we provide, the control contractor provides LAN network controllers that control this LAN and communicate how we feed data back up to this one. And then we have bus networks, which are a controller that control these lower buses or LANs or networks. The bus, we'll explain this in the architecture video, but basically there's different kinds of lower level networks. And these are the controllers that are hanging down in there. Today we're going to talk about these and these. So we'll talk about their detail. This is a VAV controller, this is a unit controller, and these are small controllers. So controllers, we have LAN controllers, types of equipment controllers, application specific, which basically come pre-programmed. They do need to be configured, but they're already programmed. A programmable controller, fixed point. They got a certain number of points on them. Many configurable or point density. Many configurations of that. Like might have one that's 4DO, 2AO, 2DI, and 2AI to run a small fan coil or something. You might have 8 UO, universal outputs and universal inputs, which you can configure one way or the other. Or you might have very large. You might have 64 and 64, very large point capacity. Programmable controllers can have expansion modules that allow you to add points. So like I say, if you got a 16-bit controller, you can add you got lots of horsepower, 16 bits, so you can basically probably add some more points into that. VAV controllers that they'll have an onboard actuator, or it might come without an actuator, just so you can use a remote actuator. Every type of controller has input-output points to connect to sensors, control devices, equipment, motors, valves, and dampers. Quantity of each type of point will vary from each type and size of controller. Point type again is UI or DI, which is the output, input, digital inputs. UI or AI analog inputs. UI or DO digital outputs. UO or AO analog outputs. And each controller manufacturer has different types, sizes of controls with different point counts. Each controller has limited capacity for analog points. The analog one is the one that analog outputs take horsepower to run. They have to have enough capacity to run these pretty robust loops within a unit. The rest of these are pretty simple to bring them in, do an A to D conversion, and spit them out. But this one has a lot of logic based into it. It's going to take some horsepower. So this one's what limits. You can have a controller that might have 4 points, 4 analog outputs, but it may actually be that you can't actually run 4 complex analog outputs. So here's a typical controller. All vendors are different, look different. This happens to be an Allerton controller. I happened to have a job the other day doing doing submittal reviews, and this contractor did an excellent job. Very, very good graphics. So I thought I'd use those to make things clear of how we look at a submittal. So that's why I'm using this one. Point counts are from 8 to 64 up to 128 with expansion modules. This happens to be on this controller. This happens to be a controller with an expansion module on it. So this has the LAN connections up here, has the power connection coming in from the controller. It has 6 BO outputs. It has 3 universal inputs, all on the motherboard, on the main controller. Here's the MAC address to put in for the controller so that it knows where it's at on the network. And of course, this is the control and manual switches. Then on the expansion module, you have another 6 binary outputs. You have another 6 universal inputs and another 5 UIAO, inputs, outputs. It's kind of weird to have universal in and outputs, but it has those. And here's a 24-volt AC outlet in case you have devices out there that require 24-volt AC to run, like a transistor or something, but it doesn't require a whole bunch of power. Requires a whole bunch of power, you have to use an auxiliary transformer, but you have 24 VAC right aboard, and you also have 20-volt VDC down here in case you have a device that needs DC. So there's certainly amp limitations, but this will allow you just to wire it right off the controller rather than putting a DC powered supply. So that's very handy to put when you're doing installs. So that's down here is that 20-volt power supply. All vendor controllers are different. Using this Allerton unit controller as an example, all have power, LAN connections, and various types of I/O input and output points. Point counts are from 8 to 64 and up to 128. And this again is one of these smaller unit controllers. This is the LAN connection. This is the power connection. 5 BO binary inputs, 3 universal inputs, and 3 UI-AO outputs. So we can have 3 universal inputs and 3 universal outputs, analog outputs. So this is a real small unit controller, and it would work for that. It's the MAC address again. This is the controller mounted. Here's the 24-volt power, and it has 20-volt DC power down at the bottom also. So here's a VAV controller, an Allerton VAV controller. You can see it has an actuator built right on it. It has a LAN connection down below. It has power connections up the top. It has 5 SSR outputs, solid state relays. So this would be basically triac outputs. 1 IMSET connection and this sub-sensor network. So you can have different sensors on without burning points. It has 7 UI-AO inputs and outputs. Now, just because this has 7 AOs, this cannot run 7 analog outputs. Just so you know, it's got This is counting on you to use one analog output for a hot water valve, right? And maybe a couple of inputs. It's not intended to have 7 outputs. Just because you can doesn't mean you should on this one. Then the RS-45 Modbus, in case you need a Modbus connection. 20-volt DC output and damper actuator. And this is the pitot tubes to go for the velocity sensor on the VAV box. So almost all manufacturers have a VAV box actuator like this that allows for pretty simple installation in the field. When DDC first came out, systems didn't look at all like each other, and they were drastically different. And the game back then, of course, was to write a spec for an engineer that was proprietary, but it seemed not. Well, you put little gotchas in it that you could do, but your competitor couldn't. Well, those days are pretty much gone. Pretty much everybody can do what everybody else can do. Some are better than others, some are higher quality than others, some are faster than others. But basically, pretty much every system can do similar things. Control submittals for controllers. This is what you're going to, if you're a commissioner, you're going to look at submittals, or you're an engineer looking at submittals. This is what you should see. First, you should see a cut sheet on the controller. This is the manufacturer's data to tell you about the cut sheet. And here you can find out how many bit rate it is, what bit rate it is. Is it an 8-bit, 16-bit, 12-bit? What is it? And it'll tell you that in here and tell you the point counts, and it'll, in details when you read it, it'll tell you what the limitations on those points are. So this is the first thing we look at is called the cut sheets. Now, it's pretty typical in the industry that control contractors have 2 parts that are submitted. One is all the equipment they're going to use, and the second is the control drawings. Now, the control drawings take some time to do, so you need to understand that they normally submit all the cut sheets first in the first phase submittal, and the next phase submittal is all the control drawings with the sequences and all that stuff. The problem is some control contractors are so bad at getting those drawings done that they'll be halfway done with the job before they get the control drawings done. You need to not allow that to happen. They need to have approved submittals before they start installing the project. I know sometimes that's not possible, but it's really difficult to have a job where you don't have approved drawings when you start to build it. Control panel enclosures. You need to see what they're going to use for control panels. Control panels come in all different types, sizes, come in different NEMA ratings. NEMA 1 for indoor. They're going to have NEMA 4, NEMA 12 outside, NEMA 4X for water. There's all kinds of them, and you need to just see what you're going to get there. And a control submittal unit diagrams. Now, this is a little bit harder to see, but this is basically a schematic diagram of an air handling unit. And you can see that it has the fan, the coil, some different devices out here, and then it has some typical wiring diagrams or diagrams of what's going to happen here. And this could be a copy of basically what the engineer had on the drawing with a little more detail of what they're going to do. And then this is a control submittal control wiring diagram. It shows the controllers and how they wire up to which device. This is the installer needs this, and the owner will actually need this, and it's really good to have. So basically this shows the different components that are inputs and outputs to this device and how they're wired. This is a control submittal control wiring diagram. This is the one I said I got this submittal and I was really happy with. It's very good. And this shows an allergen controller. It shows the different input devices coming in and how they're actually wired up. I mean, the reason this is good is because an installer has to almost really screw up to make a mistake, because it shows exactly what color wire goes where, what the conductors are for this device, and it's very good, very detailed. And over here it shows what wire you wire up on a group of wires to get to this particular type of actuator. And this is actually what the controller, the field guy, needs. He doesn't need to waste time trying to find documentation to figure out how he needs to wire it up, because if he wires it up wrong, it takes some field time. It's a disaster job. So the higher quality your submittal, the higher quality your job will be in the field. This is control submittal interlocks and device wiring. So this shows you different devices coming off the controller. This shows you these different input devices different kinds of devices. I don't know what these are right now. This is probably this is a VFD interconnection. This is probably a motor starter. Anyway, if you look at these different things, it'll tell you exactly how to wire these. These are sensors down here, and it tells the guy in the field exactly what to do. So these are very, very good drawings, and it's pretty easy for a control contractor. Once you have one of these, you have it, because you're going to use this 100 times in the future. So you just have it to plop on the drawing. You don't have to think about them once you get them done. This is a bill of materials, which is really important. So on every drawing, they should show you exactly what bill of materials they're going to use. You can tell, what the part number is and what the description is. This is a float switch on top. This is a Varic current switch. This is an alarm horn. There's just a whole bunch of things that all go into the device, and they should be on their submittal. This is a controlled submittal point list, and this point list should be complete. Now, this is a little bit of a strange thing, but on an engineer's drawing, he normally puts a control point list, and he puts a control diagram showing how this unit is supposed to work, what components it has, and then he writes a sequence of operation. Well, the control contractor actually has an obligation to make the sequence work, even if the point is not shown. Now, that may sound you could go for a change order, but I think you're going to end up pounding sand on that. For a control contractor, his obligation is to make the sequence work. That's why it's so important as a control contractor to always have a fully vetted control sequence. What happens is a lot of times engineers, especially young engineers, will, smart people, so they'll create a sequence. And I have to tell you, there's almost no new sequence under the sun. I guarantee you somewhere someone's done it and perfected it. The problem is they'll write a sequence that turns out to be almost impossible to program and almost impossible to commission. And it's not necessary. We have standard sequences. The control manufacturer has standard sequences. ASHRAE Guideline 36 has standard sequences. And as an engineer, you should always stay with standard sequences. You do not need to create a exotic sequence. And I have seen some doozies, ones that are just impossible to program. And why is that? Well, the problem is it's not that your smart sequence wouldn't work. It's just that the control contractor has never seen it before, not quite sure what to deal with it. The programmer's never seen it, and he's got to figure it out, and he may not figure it out correctly, and the installer may not get it correct, and the commissioner may not get it correct. So what I always tell engineers, if you're going to create a new sequence, you need to put enough money in your job that you have time to train everybody downstream, including the operators, when we get to the job, to make sure it operates correctly. And, of course, they never have that kind of money in their project, so it really should not be. You should use standardized sequences everywhere you can. You can't everywhere, but that's what we should do. This is a control layout drawing, plan layout drawing. So this shows a floor plan and shows you where all your devices, your boxes, and what your control LAN looks like and where your LAN's going to go. This is really helpful to tell. And then you also need to have control submittal panel layout drawings, which means in an electronic control panel, you have different devices layout, you have different control components, and he needs to have these laid out. It may be more complicated than you think. It may have a back plane, it may have a front plane. In other words, it may be a special door inside here that has a whole bunch of switches and lights on it, or they may be in the front face, but either way, you don't know. So this happens to show gutters around the outside, and wire gutters are important to keep the wires from being messy inside the cable, because what happens is as a commissioner, I would look at these panels to make sure it's going to be good for an operator. Can an operator determine what wire goes where and to what device, in case he has to troubleshoot it? So these panel drawings will tell him that. Now, the sequence of operation is intended to be the contractor's sequence of operation, not the engineer's sequence of operation. Let me explain. The engineer writes a sequence of operation of how he wants the system to work in plain English. Okay? A programmer does not program in English. He programs in his system's syntax, which means he has to have a lot of things that an engineer doesn't need to put in there, like exit times, exit delay timers, exit points, entrance points, reset sequences exactly. A lot of things that the engineer does not need to detail. Well, the way it's supposed to be is the engineer puts on the drawing or the spec his sequence. The control contractor takes it and modifies those sequences to include all his special syntaxes that will provide the sequence the engineer wants. And that's what he's supposed to do. Well, 99% of the time, the control contractor simply photocopies the engineer's spec and paste it in his submittal. And the reason they do that is so they won't get disapproved. It's fine, except it don't work. So as a commissioner, when I get on a job and I see that, I start asking questions. And on a job that's got a big job, it's got a lot of sequences or a complex sequence, I will ask for a sequence workshop. And we will sit down with the engineer, the programmer, the owner, and me, and we'll go through every sequence. And I'll have enough questions just to blow holes as big as trucks in that sequence, so that they have to come up with a sequence. And during that sequence workshop, we review all the issues and come up with a sequence. So this is the control that's in the submittal. So that's pretty small, pretty short video, but hopefully it gets you an idea of what submittals are and what the controllers look like and the details of the controllers. Hope the video was helpful. Have a great day, and I'll catch you on the next one. Thanks.